Hi there, welcome to my video on trigonometric identities. This video is just kind of an introduction to what trig identities are and how we can use them to kind of make expressions and equations a little bit neater and easier to work with. So lots of times we have really messy equations with sines and cosines and tangents and cotangents and a bunch of messy stuff. And lots of times we can use these identities over here to get it in terms of maybe one trig function or maybe be able to factor it a bit easier, just stuff like that. So it's nice to be comfortable with trig identities, and on tests and quizzes and that sort of thing, you'll be given these equations. So it's nice to have something to reference that you don't have to prove. So these are things that have already been proven, and they're given to you so you can use them to induce an easier method to solve your equations, all right? So like I said, you don't have to prove them on your test, but I'm just going to prove this one right here. It's probably the most common. It's called a Pythagorean identity. And you might realize that it looks kind of similar to the Pythagorean theorem, right? A squared plus b squared equals c squared. And you'll see why in a second here. They're very closely related. In fact, that's how we discovered this Pythagorean identity. But I'm just going to write up here, this is what I'm going to be proving. Sine squared theta plus cos squared theta, that's going to equal 1. Every single time, no matter what theta is, sine squared of that theta plus cos squared of that theta is always going to equal 1. Okay, so let's get into why that is. So let's imagine we have a set of axes here. Okay, and let's say that we have some triangle. Okay, I'll draw the triangle right here with some angle, and it's on the unit circle. So that just means that the radius, that was a terrible circle. The radius of this circle is just 1. So everywhere you go out from the origin, when you hit the edge of the circle, that length is going to be 1. So that means the hypotenuse is just 1. Okay, unit circle hypotenuse is always 1. Let's call this y and let's call this x. Okay, so how could we figure out what y is? Well, we know this is our angle theta. We're not sure what it is, but we're just going to leave it general in terms of theta. Y is going to be the opposite side to theta. Okay, so if we're dealing with an opposite side and we know the hypotenuse, thinking back to SOHCAHTOA, which of these three deals with opposite and hypotenuse? Well, that's going to be sine, right? So it deals with opposite and hypotenuse. So the sine of our angle theta, that's going to equal the opposite over the hypotenuse, right? Which is just y over 1. And y over 1 is just y. So the sine of theta equals y on the unit circle. Okay. It's not always equal to y because if this length if the hypotenuse was 2, well the hypotenuse wouldn't be 1 anymore. Right? It's 2, so sine of theta now would be y over 2. But when it's the unit circle, right, the radius is 1, hypotenuse is 1, so it's just going to be sine theta equals y. Okay, good. How about the x? Well, it's the same kind of idea. We know the hypotenuse is 1. We know x is the adjacent side, just like the y was the opposite side. So which trig function deals with adjacent and hypotenuse? Well, that's ca, right? Cosine. So cosine theta equals x, or x over 1, right? Because that's a hypotenuse, but x over 1 is just x. So sine theta is equal to y, cos theta is equal to x on the unit circle. Okay, awesome. So instead of writing x and y, I'm going to write cos theta and sine theta. Okay, so this is our angle theta. This is cosine of that angle theta. This is sine of that angle theta. And remember, our hypotenuse is still 1. So now we can kind of go back to our Pythagorean theorem, right? A squared plus b squared equals c squared. where A was just a side length, not the hypotenuse, B was a side length other than the hypotenuse, and C was the hypotenuse. Okay, so in this case, our hypotenuse is 1, so that's just 1 squared. Okay, what's our A? Well, our A can be either the horizontal side length or the vertical side length. So let's just go horizontal. A is going to be cos theta. So this is cos theta squared. I'm going to move this over because I'm running out of room. So cos squared theta plus, and our B is just going to be sine theta squared equals 1 squared, because cos theta and sine theta, that's just our A and our B. That's just our side lengths when our hypotenuse is 1 on the unit circle. So now, whenever we have this quantity cos theta and we're squaring all of it, we can just write it in this notation, cos squared theta. Okay, same thing with the sine. We can write sine squared theta, and that's going to equal 1 squared, which is 1. And we've just proven this identity, right? We went from seeing it in this little chart over here, right, to writing it out and actually proving that cos squared theta plus sine squared theta equals 1. And this hypotenuse doesn't have to be 1. It can be 3, it can be 10. The units are all going to work out in the end, okay? So no matter what theta is, cos squared theta plus sine squared theta is going to equal 1. Okay, sweet. So now that we know kind of how these identities are proven, right, now let's get into the idea of how we can actually use them. So let's say we have some ugly expression like sine of 2 theta, okay, times cos theta, right? And then we got minus cos 2 theta times sine theta. So we kind of switched around the sine and cosine. So we're finding the difference between these two things. Okay, it doesn't look too nice, right? So anytime we just have cos theta or sine theta, there's not an identity for that because it can't really get much simpler. But anytime we have sine of something other than just theta, like in this case it's 2 theta, or cosine of something other than just theta, it's 2 theta here, we're going to have an identity for that. Same with tan and the other trig functions as well. So sine of 2 theta, let's look for it in here. So sine of 2 theta, it doesn't look like this chart even has it, but I'll tell you right now, if you look up bigger charts, sine of 2 theta, that's going to equal 2 times sine theta cos theta. So this is an identity, a super common identity that you'll be using lots of the time. I'd say it's probably the most common other than sine squared plus cos squared equals 1. Okay, so it's a really good one to have kind of in your back pocket. So instead of sine 2 theta, let's just write that. We can replace it with 2 sine theta cos theta because it's the exact same thing. Okay, remember, and we still have this cos theta here, right? Because sine 2 theta is this part here, and then cos theta we just kind of have to bring down for the ride. Okay, and we're subtracting cosine 2 theta times sine theta. Okay, so an identity for cosine 2 theta, I didn't realize the chart didn't have it, but an identity that we can use is cos of 2 theta is 2 cos squared theta minus 1. So this is another pretty common identity. Okay, so instead of cosine of 2 theta here, we can just plug in this part right here. Minus 2 cos squared theta minus 1, right? And all of that's being multiplied by sine theta. Okay. So now let's kind of expand this out. This negative's going, actually let's expand 2 cos squared theta into sine theta, negative 1 sine theta. So we got 2 sine theta, zoom in a bit here, cos theta times cos theta. So instead of cos theta times cos theta, let's just write cos squared theta, because that's the same thing. Okay, minus 2 cos squared theta times sine theta. Not really a way to condense that, so let's just write 2 cos squared theta sine theta. And then we got this -2, or we got this -1 times sine theta. So this is going to be minus sine theta 2 cos squared theta. Or, my bad, sorry. Just negative sine theta is going to be what's on the inside there. So we just distributed these two things into the sine theta there. And now let's distribute this negative into each number here. Okay, so this is going to be 2 sine theta cos squared theta minus 2 cos squared theta sine theta, and then negative times a negative is just plus sine theta, right? And see how we have 2 sine theta cos squared theta minus 2 cos squared theta sine theta? Even though these orders are mixed, they're still multiplying. So these two are the same thing, and since the second one is subtracting from the first one, the first two terms are gone, and we're just left with sine theta. So our answer is literally just sine theta. So we started with something that looked super ugly. People probably wouldn't have any idea how to approach this if they didn't have these identities, and that's equal to just sine theta. Like the literally the simplest term that you can have in trigonometry, sine theta, comes from something as crazy as this, just using trig identities. So there are definitely powerful tools to have in your toolkit. Let's just do another example here. Okay, so let's say we have 10 sine 6x cos x, or cosine 6x, okay, plus 4 cosine 6x sine 6x. Okay, so these kind of the common factor of these is sine 6x cos 6x. They both have that in common. So if we have 10 of them here and 4 of them here, we can just add 10 and 4 together. We're going to get 14 sine 6x cos 6x. Okay, so we're one step into it. We just combine like terms there. We got 14 of them. And one thing I notice is, remember the identity we used in the last question? Sine of 2 theta equals, that's going to equal 2 sine theta cos theta. So see how we have sine theta times cos theta here, sine of an angle times cosine of an angle here. It doesn't matter that theta and x are different. What matters is that it's like sine of an angle times cosine of an angle. So we can kind of relate those two together. So just bringing this question down here, if we factor out a 7, right, and kind of get it so there's a 2 left, because 7 times 2 is 14, right? And we just get our original kind of question back. But if we factor out a 7, see how we're left with 2 sine 6x cos 6x? And we can relate that to the identity 2 sine theta times cos theta. So in this case, our theta is just 6x, right? Our theta is just 6x, but other than that, it's the exact same equation, the exact same expression. So the 7 is still going to be on the outside, but on the inside, since 2 sine 6x times cos 6x is equal to sine of 2 times 6x, right? Using that identity, sine of 2 times 6x, we can simplify this by just writing 7 times the sine of 12x. right? So if we didn't factor out the 7 and leave this 2 sine 6x cos 6x inside, we wouldn't have been able to use this identity. But since we're good with our identities and we recognize that we can manipulate it, so there's going to be a 2 left in here, 2 times this stuff, and that's like our identity on our sheet. We can say that this stuff right here is equal to the sine, right? We're getting rid of this cosine. It's just the sine of 2 times whatever the inside is. Okay, and we can get it down to just 7 sine 12x. So there's too many identities to go over in one video, but that's kind of the basic idea. You can do it where it's like um, if you have like the sine of pi over 12, right? That's called a sum and difference identity, where I think it has it on the sheet here. Um, you can figure out like what theta would have to be, like pi over 2 minus what? That's going to equal pi over 12. We have to figure out what theta is and then just plug it in um, for cosine theta, and we can figure that out. And we can do a couple of different things for different situations, but there's just too many, like I said, to go over. So that's kind of the basic introduction into how we use identities. So yeah, in my next video, I'll kind of talk a little bit more about them, how we can prove two things to be equal using identities, but that's just an introduction, and I'll see you in the next video.